Is there an edge to the universe? If you kept flying straight ahead, would you eventually loop back to where you began? That question has driven scientists to search for the true shape of the cosmos. Now, we may be getting closer and closer to the truth. So, is the universe flat, or curved like a sphere, or maybe shaped like a donut? Many people believe that the universe must be infinite, without borders, but that might be a huge misconception. Imagine launching yourself into a ship that travels faster than light. You'd fly straight through the cosmos, cutting across space itself. Your mission? To explore the mysterious, uncharted frontier of the universe. To uncover the shape of everything we know. Once the answer is revealed, maybe we can put our understanding of the world, could completely rewrite our understanding of reality. When you look up at the stars, ever feel like just a grain of sand beneath the stars? The night sky stretches on endless, vast, overwhelming. But have you ever thought about it? This seemingly lecherous universe. Maybe it has its own shape and outline. He knows no boundaries. It's almost like a video game. You step out the side of the screen. We'll come out the other side. Let's move on to a very important topic. That's the infinite universe we imagine. Doesn't necessarily mean borderless. The universe may seem endless, a magical existence that can bring you back to the starting point. It's like you're an explorer, sail straight ahead on Earth. Finally, I find that you are back to square one. It's not because you went back halfway. It's because the Earth is a sphere. The discovery that the Earth is a sphere. Back then, it was the human view of the world, completely turned upside down. To understand the shape of the universe, can it also have the same explosive effect? We are in the process of exploring. Have to think carefully. Is this real or not? Are we living in a closed space? And we'll never be able to prove him. This question will always follow us. This amazing cosmic journey. Because today's content is not just scientific exploration, filled with philosophical thinking. Before studying modern cosmological models, let's travel back in time. Let's see how humans understand the universe step by step. Athens, 2,400 years ago. If you were sitting next to Aristotle, watching the night sky with him, you will know, in the concept at that time, the universe is finite, because people imagine the universe as if the Earth is at the center, surrounded by the sun, the moon and the stars. Aristotle said the sky must be finite, if wireless. Why is he spinning around? The idea seems simple, but it reveals ancient people's understanding of the shape of the universe and deep perception of movement. The Greek thinkers of the time look up at the stars at night. The stars seem to orbit a fixed point. This situation, naturally reminiscent of a star model, just by making a simple and detailed observation, the Greeks made it a cosmological model that can last for nearly 2,000 years. Aristotle's model, not just physical reasoning. It has philosophical and theological implications. In this model, cosmic order, hierarchical, Earth city center. Humans are also at the center, the further away from the center, the closer to divine perfection. Planets are perfect representations of this. This concept not only explains scientific phenomena, it also allows people to find their place in the universe. If you lived in that era, I guess I will also feel this model explained the order of the sky clearly. But in the 16th century, Gobaini was born, put the sun in the center. That's a big deal. Not only did he rearrange the sky, and the central place that humans think they occupy can be moved. This revolution, it's like opening a box full of questions. Pandora's box. If the Earth were not in the universe, where is the boundary of the universe? What shape is it? It's a puzzling question. In the 17th century, Newton took a crucial step. He came up with the law of external gravity. This law states that between any two objects with mass, there is mutual attraction. Their size is directly proportional to their mass. inversely proportional to the distance between them. But Newton worried about an infinite and static universe. Attractive force pulls all matter to one point. You close your eyes and imagine millions of stars are attracted to each other. How does the universe remain stable? Like on a perfectly flat table, put billions of marbles. How could they miraculously not get together? It's still scattered. Newton didn't solve this problem completely in the end. This also shows that the concept of infinity hid a lot of headaches. However, the real big change also depends on Einstein. The general theory of relativity was developed in 1915. This is not a simple new equation or adjust the old model. It's a reshuffling of the nature of space and time. Imagine that. You always thought you were standing flat on the same stage. Suddenly someone tells you, the stage is actually a big trampoline. It deforms under your feet. But why do objects fall down? Does the Earth revolve around the sun? Einstein made us understand it's not pulled by a mysterious force. It's that space itself is curved. Guide the object. It's like putting a heavy ball on a stretched canvas. The ball will dent and deform the canvas. At this time, roll another marble. He doesn't walk in a straight line. It deflects because of the deformation of the canvas. It's like being attracted to a big ball. So that was Einstein's idea. Let's stop thinking of attractive forces as mysterious forces. It is the result of the geometry of space-time. Einstein's new theory, to think about the overall shape of the universe, opened a new door. Two important concepts, curvature and topology, are also introduced. Suppose you examine a small piece of orange peel. From this small proportion, can you tell if it is curved or not? This is called curvature, is a local property of space on small scales. Can you tell us how space curves? If you look back at the whole orange, you can see it's a closed sphere with no edge. That's the topology, how our space is connected on large scales. To better understand the shape of the universe, let me tell you the story of the little ant. You'll understand. There's a strong ant that lives in the envious belt. He's here every day, seemingly ordinary, looking for food on the surface. One day, he suddenly decided to keep going. Don't look back to explore the world. Unexpectedly, after a while, he actually went back to the starting point. But he was on the other side of the bag, and he gets confused, and he goes back to where he started. This time it was on the original side. Ants don't know. He lives on one side of the envious strip. He told us, it's normal to see his world from a partial perspective. But overall, this strange topology, let him go back to the starting point without turning around. If our universe, you have this strange topology, then let's keep going in one direction. It is possible to go back to the starting point. It's this topological property. We can use it to describe our universe. That's what we're going to focus on. We already know that the universe is super big. How can we measure its area ratio? It's like, you want to know if the place you live in is flat, still spherical, but you never left the universe. If you were a space detective, the task is to determine the shape of the universe. But you can never see the whole universe. So how do you go about finding clues? This is cosmology. Models come in handy. Three famous astronomers, Arthur Friedman, Howard Robertson, Fuff with Edwin Hobart Walker and others. Model, although the name sounds complicated, in fact, it is described in mathematics. How does the universe change over time with his substance? What does it have to do with energy content? There's a key number here called omega. He is not a planet. It's not a mystical force. It's just a normal number, but that's the number. But it determines the fate of the universe. If omega is too small, everything will continue to expand. If it is too big, everything will fall apart. Only just right. The universe can be balanced. And there's very little of it. The result is the attractive force of inflation. In the Euclid rivers we learned about in school, You draw two lines on the equator of the Earth. But you know what? This actually only works in flat spaces. If you change to another place, things are very different now. The interior angle of a triangle is always 180 degrees. Imagine that. Both lines point north. The two lines intersect at the equator, forming two 90-degree angles. And look at the North Pole. There's a corner there. Although it is not 90 degrees, but certainly not 0 degrees. This way, the interior angle of this triangle must be greater than 180 degrees. This is spherical geometry. The Earth we live on is a good example. On the sphere, the interior angle of a triangle is greater than 180 degrees. That's because the sphere has a positive curvature. On the contrary, on a hyperboloid surface, the situation is completely different. The hyperboloid is sort of like a saddle. It has a negative curvature. On this surface, the interior angle of a triangle is less than 180 degrees. It seems counterintuitive. It's actually a direct result of the curvature. These geometric shapes are not mathematically curious, because they have an idea about how light travels through the universe, affect what we see when we look up at the stars. Something to do with this. So how do we determine what kind of geometry our universe is? What about shape? Scientists have an idea. That is, to observe the cosmic microwave background radiation, except for the WAMP satellites from 2001 to 2010, and the Planck satellites from 2009 to 2013. The two satellites. It was specifically designed to solve this problem. These satellites precisely map the cosmic microwave background, because this is after the Big Bang, 380,000 first light of day. It's like you want to take a picture, photos of candles thousands of kilometers away. Have to. Accurate to the point where the temperature changes by only a 10,000th of a degree. The difficulty can be imagined, but these satellites did. The cosmic microwave background radiation data they got, it's like a picture of a baby universe. Although we cannot directly see the present universe, but it contains clues to the future. By analyzing the fluctuation statistics of radiation temperature, cosmologists can determine the geometry of space. It's like you can hear sounds, infer that the object is the same shape, but the measurements surprise scientists. The Mach is approximately equal to 1.002. His error is very small. This suggests that the universe is almost perfectly flat. Available in 2003, a scientific paper completely blew up the cosmology community. French astrophysicist Jean-Pierre Luminet and his research team, when analyzing cosmic microwave background data, found generally speaking, temperature fluctuation. There should be patterns of various sizes. Small fluctuations and large fluctuations are interrelated, but they observed areas in the sky above 60 degrees. Temperature fluctuations are irrelevant. It's like watching the waves from the ocean. Normally, there should be both large and small waves, but there are only small waves in the sea. Never seen a big wave. You must think, is this sea too small to hold big waves? So Lumi, Nirvana and his research team agree. Is the universe like this? It's actually smaller than we thought. What if the universe were like this? You keep going in one direction, maybe back to the starting point. That would explain the anomaly. To explain this, they came up with a bold model. Say the universe might have something like topological structure of Poincare dodecahedron space. The name sounds complicated. In fact, it means the universe is like a corpse with 12 pentagonal faces. Imagine you walk across a face. Will soon be reborn on the other side. And with a little spin, it's a fascinating idea, if true. The actual volume of the universe, probably much smaller than what we see. The universe we see could be bigger than the universe itself. This is what Luminet called the concept of a curled universe. If so, We may see the same galaxy multiple times, arriving on Earth from different directions at different ages. Like the mirror house in an amusement park, the mirror reflects countless images of itself. It makes you feel like space is infinite. In fact, the room size is limited. How do we test this hypothesis? Scientist. In the light at the far end of the universe. Looking for clues. Because the universe is really like Poincare, complex topologies like dodecahedron space. It should be there, in the cosmic microwave background radiation, leaving an observable imprint. It's like you're in a fog forest. The fog limits your vision. You take pictures around. If the forest is smaller than your field of vision, will repeat, then you might see it in the photo. The pattern of the tree appears multiple times in different directions. Similarly, if the universe were to fold itself up, cosmic microwave, the field of view of the background radiation will form circles. We should be able to observe the temperature fluctuations on these circles are the same, because they are actually the same wave, viewed from the opposite direction of the sky. If you find these circles, it is equivalent to giving non-trivial topology found evidence, but the researchers searched for half a day. The results are still ambiguous. Why does this happen? It turns out that the cosmic microwave background radiation, it's like listening to someone whisper in a crowded room. It's so hard to hear. Researchers have to analyze millions of pairs of possible circles. All directions, all possibilities have to be considered, like looking for a needle in a haystack. It was incredibly difficult. Future artificial intelligence and machine learning might be of great help us find patterns that traditional methods may have missed. In recent years, scientists studied the shape of the universe with the new perspective. In 2019, researchers at the University of Manchester in the UK, with data analytics from the Planck satellite, point out the universe may not be as flat as a sheet. It's more like a closed sphere, but the closed universe. This idea still needs to be further validated. Currently, the scientific consensus on the shape of the universe, it's still flat. By 2021, there are scientists. A new approach is proposed to explore the topology of the universe. That is, by seeking specific signals in the cosmic microwave background radiation. This method may reveal to us the true shape of the universe, provide new clues, and that's something to look forward to. Actually, the shape of the universe is not just a scientific question. It may also have an impact on our daily lives. For example, if the universe is finite, then the starry sky we see, maybe it's just a part of the universe. And the real universe, it's smaller than what we've seen. This understanding, it may change our understanding of the universe and humanity, perception of one's own position. Understanding the shape of the universe also helps us better understanding the evolution of the universe. So scientists are always developing new statistical methods to predict the future of the universe. So what is the shape of the universe? The debate among cosmologists about these issues, pretty intense. Some people say the shape of the universe is a matter of fact, can be solved by observation. Some people think different regions of the universe may have different topological structures, is part of a much larger multi-source universe. No matter what, these ideas, let's rethink the infinity of the universe. The universe is topologically finite, but for the observer inside, may seem infinite, although we keep exploring, but never reach the boundary of the universe. The difference between wired and wireless, breaking our conventional understanding of space. Space can be finite and boundless. This is the amazing universe we are learning about. So what shape do you think the universe will take? You are welcome to let me know in the comments section.